And now we're going to look at something that's sure to put a little spring in your step, simple harmonic oscillations. I broke this video into two parts because there's a lot of concepts to cover. So suppose you've got a block, it's going back and forth, it's attached to a spring. We'll define this as the plus L axis, you can use X, doesn't matter. L0 is your equilibrium, that's just where it starts, and I'm going to label this as L equals 0. So we're going to write an equation for the energy of a system. The block's going to move back and forth, potential energy for gravity for good measure, and this is your spring potential energy. Let's determine the acceleration. So to do this, we use dE dl. And remember, the reason you take the derivative with respect to space or a spatial coordinate is because you're going to get acceleration. So we get from the kinetic energy, of course. So this part, the derivative goes to ml. This is dy dl. Dy dl, what's that going to do? Well, it's 0, and it's an isolated system, so this term's going to go away, that's going to go away, and all you're left with is this nice expression that we can solve for the acceleration in the L direction. Let's take a look at it. Let's solve for this. And we get A equals minus k over m L. But let's delve into what is A. What is acceleration? And acceleration is the second derivative with respect to position. Now wait, so I've got a formula whose second derivative over here is equal to the first derivative, or the second derivative is a linear function of position, and this is going to have some special properties. But first we need to wonder what function has a second derivative that is equal to -1 times itself. Second derivative. Sines and cosines. Here we go. You could also use exponentials, but you can relate exponentials to sines and cosines. So we're just going to stick with sines and cosines. And we're going to introduce this new term, angular frequency, which is how fast your angle changes in radians. So what I've done is you can verify that a solution to this equation is that your length is a function of time. So where this block is located, the length of your spring is equal to your equilibrium length times however far you pull it back, that's the amplitude, we'll talk about this in a minute, times some angular frequency times time plus some offset. We defined this as the square root of k over m. So going back, this would be omega squared. And the reason why is going to show up in a little bit. So what does this all mean? Let's take a look at the various pieces. LE is your equilibrium position, A is your amplitude, so that's how far you've pulled that spring back initially. This phase is just the proportion of the oscillating function that varies with time, that's this piece right here. And this phase constant is an offset, so sometimes you'll walk in and the spring might not be exactly at 0. That's okay. That's where that phi 0 comes in. You can solve for phi 0 based on your boundary conditions, and there's a nice example in your textbook that I would look at. Here's a little graphical interpretation. Amax, how far you pull it back, and then it just goes through. Here we don't have a phase shift, and you can tell because we're starting at 0, which at t equals 0, sine of 0 is 0, so that's how you can tell there's no phase shift. If this was offset, say we were over here, all right, and we did this, well, now your offset is a factor of minus pi over 6. The negative is going to be interesting when we come into play. But that just means that t equals 0. Instead of being 0, now you're offset over here. So just like we've done throughout the whole semester, let's look at the energy of this system. So the potential energy is just your spring potential energy. And if we relate this, now instead of L, we have this L of t, which is related to this formula. Oh, look, those LEs are going to cancel out. That's nice. And then we'll get the potential energy from this spring is now given as K, your spring constant, times A, your amplitude, how far it pulls back, squared, sine squared omega t. All right, well, that's nice. And now for kinetic energy. So velocity is the derivative of position. So we'll take the derivative with respect to time of our function for position, and we'll get A omega cosine omega t. So this omega, when you take the derivative, comes out, you have to chain rule it. Phi 0 doesn't do anything because there's not a function of time. And then we'll say that this, your kinetic energy, is just 1/2 m v squared. And this is v squared. All right. So now Oh wait, m omega squared. Well, this is just, ms omega square root of k over m. We square that. That's just k. Alright, so now I've got k cosine squared. Sine squared and cosine squared. What can I do with this? Well, we'll show you. Or you may have already known. You can try it yourself real quick. So if we add it, we notice that these arguments are the same, and sine squared plus cosine squared of the same argument just gives you 1. Your total energy of the system, assuming it's frictionless and you're not losing energy to energy dissipation, is just equal to Ka squared. So however far you pull it back and the spring constant, that tells you how much energy your system is going to have throughout, well, as long as you've got that system and you're not losing energy. Simple harmonic motion, that's the term we're going to use to define all this. It's an oscillatory motion where the acceleration is linearly proportional to the displacement. It's going to go back and forth. It's going to wee, boing, 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 back and forth like a spring. It occurs for systems in which the translational kinetic energy is proportional to the square of the displacement of the system from its equilibrium point. So we're looking at position squared, which means, back to looking at this block. Here's your energy. We'll take the derivative with respect to position. This one goes to ma, dy dx. Again, it's not moving vertically. And this is just going to be kx. All right, so I get acceleration is mkx, or acceleration is negative k over mx. Oh, but we said we had a special word for k over m. Well, more importantly, the square root of k over m, which is omega squared. And we said that acceleration is the second derivative of position. This is your simple harmonic oscillator equation. Okay? For simple harmonic motion. Anytime you have an equation that satisfies this, you can view it as a simple harmonic oscillator, or it looks kind of like a spring. One last key concept that I'd like you to go before we look at the example video, and I encourage you to do that, is we're interested in the period of oscillation, how long it takes for this block to do one full thing. So that would be one complete going this way and this way, one complete back and forth. So if we look at this cycle is going to repeat based on this angular velocity, and we will get the period time for this oscillation, it's measured in seconds, is 2 pi over omega. That's neat. And sometimes we will also look at frequency, and we define frequency as 1 over the period, or the number of cycles. And this is in hertz, or 1 over second. That's the frequency. How many times per second this oscillation goes back and forth. I hope that was helpful. Tune in for the next video. We'll talk about some examples and how we actually use these concepts.